Hi everyone, in this video I'm going to go through question by question this practice multiple choice from 2012 that we took. This is going to go in detail through each question, so feel free to skip around a little bit if there are specific questions or specific ones you want to look at. So, starting with number 1. Which represents the greatest standard deviation? The greatest standard deviation, remember standard deviation measures average distance from the mean. And so we're asking which one has the data points that are farthest from the mean on average. These all have a mean of about 5, but the ones that are farthest on average from that mean of 5 is B, because all the points are either on the really high end or the really low end. So that's the one with the largest average distance from the mean. Next. Approximate interquartile range for this one. Interquartile range, remember, is Q3 minus Q1. And if we can read our box plots, this is the minimum, this is Q1, this is the median, Q3, this is the maximum, and there's an outlier here. So Q3 looks to be at just under 20. Q1 looks to be about 4. So about 20 minus 4 would be about 16. That's approximate, but that's the only one that's really close. So Q3 minus Q1. Next, this is making sure that you know what the difference between skewness. Remember, skewness is the direction of the tail. So there's the shape, and that's a skewed left distribution, because the things that are causing the skewness are these values, these extremely low values out on the left. So it is being skewed to the left. That's number 3. Next. Bank surveyed all 60 of its employees. So if we're talking about confidence intervals and generalizing the results, you can only generalize the results to the ones at the bank, and we don't need to do any inference procedures like confidence intervals or hypothesis tests, because we took a census of everybody. So we don't need to estimate what the parameter is of all the people at the bank, because we asked all the people at the bank. Number 5, they like this question. They like the question where you're asking for the median from a histogram. So we have 175 patients. So that means the median is the middle value, so 175 over 2, about halfway across the list of values. That means it's at 87.5. So that's about the halfway point. So we go until we get to about the 87th data point. Well, we have about 80 data points, and then here we have another 50 for a total of 130. So the median has to be somewhere in between 5 and 10, so 7.25 would be the only plausible value on that list. Next one, number 6. Which of the following must be true? Remember that for the quartiles, these are the 20, basically like 25th percentiles. So this is in sections of 25. So between the minimum and Q1 is 25%. Between these is 25%. Between here is 25% of the data. Between Q1 and Q3 is 50% of the data. So that's what this question is asking about. And the only one of these that is actually true is A, which is saying that this is the median, which means that about half the points should be above it, half the points should be below it, which is what choice A is saying. The other ones give incorrect percentages or can't be determined from the quartiles. Next one, 7. Let's talk about the males first. The male grizzly bear with a weight of 530 pounds. Well, for the males, we have a mean of 500 and a standard deviation of 50. So my z-score formula is value minus mean over standard deviation, so that's going to be 530 minus 500 over 50. And that's going to be 0.6 when you calculate it out. And so now I want to go over to the females and say I want to know where the z-score of 0.6 has to be. So I want to know what value will give it that. And for the females, the mean is 300, standard deviation is 40. Mean 300, standard deviation of 40. Solve that for x, and we get 324. So that's using our z-scores to jump between different distributions. Next one, number 8. Oh, this is one that I've talked about a lot. It gives my standard deviation. So it's asking about standard deviation of the new variable. So here's the standard deviation for x, 5.76. And it's asking if I take y equaling 75x minus 100, well, standard deviation, if I multiply all the values by 75 and subtract 100 from all the values, remember that what that's going to do to the mean, it's going to multiply by 75, subtract 100. To the standard deviation, it's going to multiply by 75, but it's not going to subtract 100. Because if I'm thinking about, here's how spread out my data is, if I take it and shift it over 100, it's still as spread out as it was before. It's just been moved over here. So the subtracting 100 doesn't affect the spread. So all you need to do is do 5.76 times 75, and that's your answer. Not the subtracting 100 for that standard deviation. Next one, number 9. This one's pretty heavy formula-wise. I want the margin of error to be 2.7 percentage points. Remember, margin of error, it's the part that comes after the plus or minus in the confidence interval. So it's the critical value times the standard error. That is my margin of error formula. Critical value times the standard error. And so in the case of this one proportion, which is what we're estimating, it's one proportion. So with one proportions, we're using z-score for my critical value times my standard error for one proportion is p hat times 1 minus p hat over n. So I can plug in my values. I want my margin of error to be 2.7 percentage points. So as a proportion, that's going to be 0.027. And I'm going to be solving for z. I want to know what the z-score is because that will tell me what my confidence level was. Remember, that's the part that the confidence level is relevant for, is the z-score in the formula. So we're solving for the z-score. P hat here is 60%, so 0.6 times 1 minus 0.6 all over our sample size was 900. And if I solve this equation for z, z ends up being about 1.65, which if you remember this value or test out your inverse norm or use normal CDF, however you want to do it, you'll find out that 1.65, or you can even use the table, you'll find out that that's for a 90% confidence level. Number 10. Manufacturer wanted to determine if the two different cover designs will generate more sales. So here's how they designed it and said whether, and we're trying to see whether we can make a good conclusion. And the biggest thing is that cause and effect, you can't establish cause and effect unless you have the random part of the process. Random assignment in the experiment. And in this case, we do have the random assignment. So we randomly assigned them to sell CDs to the 35 of the CDs for the different cover lines. So that means we can establish that the variable that is causing the distinction is the different cover designs for these CDs. Next one, number 11. Number 11 isn't blocking by some other variable aside from the detergent that we think has an effect. We're not just observing. It's not an observational study because we're not just, putting a detergent in and observing the effects. We're not just asking them what detergent would we use. We are determining ourselves whether to use detergent A or detergent B. This is a completely randomized design. Completely randomized design is whenever you have part of them going into one group, part of them going into another. In this case, some of the 20 are getting A, some of the 20 are getting B, and we are randomly deciding which one is which. That's a completely randomized design. Next one, 12. Response bias. First off, tweaking with the sample size has to do with variability and not bias. So if we have a biased design or a biased method to do our experiment, and we just ask more people with our biased method, we're still going to get bias. So A, B, and C are out. Response bias is about anything that affects how people are going to respond to the question. And so we want to tweak and make sure that we are minimizing any effect that on how people are going to answer the question, and so that is choice E. Other examples of response bias in other than question wording include the topic that they might be embarrassed to admit something, the platform that we are asking the question over, whether the responses are kept anonymous, the person who is asking the question, whether that might influence how they respond. Anything that influences how they're going to respond is response bias. 13. This one is skewed to the right because if I draw, what my normal curve would look like. Okay, so let me just draw. Let's say that it would, we would think that it would be normally distributed. Well, mean is 5 and standard deviation is 3. So let me draw that real quick. So a standard deviation to the right, another standard deviation to the right, standard deviation to the left, another standard deviation to the left, and we're at -1. Well, a rabbit can't weigh -1 pounds, so this left tail here is basically taken away until we get to 0, and maybe those data points get piled on here, and all of a sudden we have a distribution that's skewed to the right, because the smaller values that would be in that normal distribution are not possible to get in this case. Uh, 14, they threw it out. They did not score it, so I did not affect it in the scoring when I scored your multiple choice. 15. In 15, the reason that B is not a concern, usually it would be if they were pulling numbers out of the phone registry and calling people at random, then unlisted numbers would be a concern. But because they are calling random phone numbers, and they are not pulling it out of a listing or a phone book or anything like that, any phone number is possible to be called, not just the ones that are listed. So that is not a concern. The others are concerns for bias. 16. 16 asks for the probability that the device will not fail. So in other words, the entire device needs to work. And in order for that to happen, A has to work, B has to work, and C has to work. So in order for all of those things to happen, we need the probability of A working times the probability of B working times the probability of C working. Multiply because they all need to happen, so they're AND probabilities, so we're going to multiply them. Probability that A works is 0.99. Since 1% of the time they fail, that means 99% of the time it works. Probability that B works is 0.97. And the probability that C works is 0.96. So we multiply those together. That gives us our answer. "17. Point estimate in the confidence interval. The way that the confidence interval can be structured a lot of the time is estimate plus or minus margin of error. Right, so the thing after the plus or minus is called a margin of error. The thing before the plus or minus is this point estimate. That is this estimate right here. So if I write the confidence interval from 3 to 9, for example, I could rewrite that as 6 plus or minus 3. So in that case, 3 is my margin of error, and 6 is my point estimate. So it is basically the middle point of the confidence interval. It's the place we're building the confidence interval around. So here's my confidence interval, and I want to know what the middle point of that is, and it's going to be C. That's where the middle of the confidence interval would go. You can rewrite this as 0.08 plus or minus 0.032. That would be the way that this confidence interval would look. And so that 0.08 is the margin of error. Next. Population being at least 10 times the sample size is the independence condition. And another way to say independence is that the degree of dependence is negligible. In other words, it will be close enough to independent that we can assume independence. So identifying that that's the independence condition is the idea there. 19. expected value. What is the meaning of the expected value in context? Remember, expected value is not the value you expect every time. It is, on average, in the long run, over all these games, how much is expected. That's what expected value is measuring. And so in this case, how much on average they are expected to lose per raffle ticket, so that is B. That's our interpretation of expected value. $20. $20 is a question about power. And so if you're wanting to know how this one's going to look, power. What power means is how often if the null hypothesis is supposed to be rejected, how often it gets rejected. And that will depend on what the actual distribution looks like. So I have this null hypothesis of the mean being 10. And so my rejection region is over here. But then I get told from on high, actually the mean is 8. And so I say, oh, the mean is 8. Well, 8 is over here. So the distribution is actually looking like this. So here's where I'm pulling my samples from. And so the proportion of tests that get rejected there is this proportion. That's a lot more. That's a pretty powerful test. And so basically, the more often, when the alternative hypothesis is true, the more often that's going to lead you to reject the null hypothesis, the higher the power. And so since the alternative is that mu is less than 10, the more strong an evidence there would be that mu is less than 10, the more you're going to reject and the higher the power. So that's A, because a mean of 8 would give you, would lead you to conclude that the mean is less than 10 the most often out of those choices. $21. Here are the residual plots from 5 different least squares regression lines. Strongest evidence that we can use. So this is asking about our conditions. Which one are the conditions the most true for? Well, A and B are out because they're not linear. So that leaves C, D, and E. And the biggest thing here is that D and E violate the equal variance condition. The idea that as I move from left to right across my line of best fit, the points should vary away from the line about the same amount. Right? My range of values starts to widen here and get a whole lot wider. The range of values starts to narrow and get a whole lot smaller here. So the variance, the amount that the points are spread out from the line, is not the same as I move from left to right. Whereas here, the balance of how spread out the data points are is about the same throughout. Basically, like my range or my spread from moving from left to right stays about the same. So C is your best option. That followed both the linear condition and the equal variance condition. Next. Which of the following best summarizes the meaning of the confidence interval? This is actually a question about confidence level. And the meaning of the confidence level is, out of all the samples I could gather and all the confidence intervals I can make, what percent of those confidence intervals will have the parameter? And that's B. 95% of all the samples would result in a confidence interval that has the mean in it. '23. I won't go through each choice individually here. I'll just say that the one that is true is A. If the person owns a car, they're more likely to live elsewhere in the city than to live in the downtown area of the city. So car ownership is this row. And they are more likely to live elsewhere than they are to live downtown. So there's your answer choice that's true. That's just reading the table. '24. Random sample revealed that 100 in favor. 95% confidence interval would look like p hat plus or minus our z-score times the square root of p hat times 1 minus p hat over n. Our p hat here is the 100 out of 432. And our z-score for a 95% confidence interval is, hopefully you have that memorized by now, is about 1.96. So the only one that uses that, all those is D. Hopefully you should have been between D and E pretty clearly because this is for proportions. So you should have been able to get rid of A, B, and C right away. And then the z-score for 95% is 1.96. '25. The other way to ask this question, so this is the commute time. And this is really a normal CDF question, but I'll go ahead and draw the picture as well so that you can see that. This variable is the commute time, the amount of time it takes for you to get there. And if we leave at 8:25, we're hoping to get there at 9 a.m. That's a total of 35 minutes. And what we're finding the probability that they arrive later than that so that it takes longer than 35 minutes to get there. You can calculate the z-score. You can use normal CDF. Again, the 35 or the z-score for that would be my lower bound on the normal distribution. And I should get A. '26. So 2009 survey of internet usage found that 79%. So sample size needed for the margin of error. So we're assuming that's 79%. So usually I say if you don't have a good estimate, just use 0.5 because that'll give the largest margin of error. But now we have a good estimate of the 79% because our 2009 estimate is there of 79%. So we're going to use that in the formula. And 98% confidence interval is going to give us that z-score of the 2.33. And since we want 2.5 to be our margin of error, we want to make it less than or equal to the 0.025. So that is D. Next one, 27. That is going to be that's going to be a two-sample t-test. It's not going to be paired because there's no real reason to pair this battery with this battery that's given. You want some very clear, distinct pairs if you're using a paired t-test. So two-sample t-test, and since we are asking if they last longer, that's our clue that we need a one-sided test because that's the direction. That brand A mean for brand A is bigger than the mean for brand B, so it is a one-sided two-sample t-test. 28. All right, this one was tough. So we have this two-tailed probability, and we get the p-value to be 0.44. That means that these areas put together is 0.44, which means that each of these tails are 0.22 apiece. Now, we could have gotten that area one or two ways. We could have gotten this z-score or this z-score. We could have gotten either one of those two z-scores. And so when we consider making it one-sided, I'm going to make the one-sided be less than as my direction. But I could pick either one. Less than is my direction. Either we got this z-score, in which case the area underneath there is the 0.22 from the left tail. Or we got this z-score, in which case our p-value would be all the area to the left of here, which is leaving off this right tail of the 0.22. Remember, this tail is 0.22. So we're leaving off that tail, and we want everything else. So there are two possible p-values that we could get, depending on which direction our z-score went in. '29. 29, you're just going to put this data in the calculator, right? You're going to go over to two-sample t-test, and you're going to put, here's my mean, here's my standard deviation, here's my sample size, and have it tell you what the p-value is. And it will tell you that the p-value is between 0.01 and 0.05, so D. This is really just a put it in the calculator question. 30. Since it's a two-way table, my hope is that you, and since these are all categories, I'm hoping that you narrowed it down to it being a chi-square test. And since there isn't one variable, there are two variables, that eliminates goodness of fit as well. This is a chi-square test of independence. This is also called a chi-square test of association. So when it asks investigating whether there is a relationship between them, in other words, it's asking whether these are associated. So chi-square test of association. '31. The biggest thing that trips people up on this question is that they miss the part of the question that asks if the drug had no effect whatsoever. Well, if the drug has no effect whatsoever, then the mean difference between the effectiveness of the drugs should be 0. The mean difference should be 0. So, which ones are true? Well, p-values will be greater than 0.05 for about 95% of the experiments. That should be a pretty easy one to say that it's true. Since my parameter is 0, that means the confidence interval should capture 0 about 95% of the time. That's what a confidence interval is. And then for number 2, we could draw my curve. And so here's what my samples should look like. It should be about normally distributed. The mean should be 0, which means there should be about an equal amount of values that are to the right of 0 as there are to the left of 0. In other words, the mean difference should be shown to be positive and negative about the same amount of the time. So these are all true. These are all true. And again, that's largely relying on the fact that we're saying that the drug has no effect, which means that the difference between the drug and the placebo's effectiveness should be 0. There should be no difference between the two drugs' effectiveness. '32. Margin of error here should equal t-score times standard error. T-score times standard error. And since the random sample is 2, degrees of freedom should be n minus 2, so 12 minus 2 equals 10. So inverse t with a 0.975 and degrees of freedom of 10 should give the 2.228. And then we just need what the standard error is. The standard error, we look in the slope row here, and we want the standard error of the slope, which is the 0.745. No other fancy footwork with the formula. That's all it is. (33). All right, this is an expected value question. Let me do it for these. So if I leave it blank, all right, this is my benchmark. If I leave it blank, my expected score is 2. Because I left it blank, I get 2 points. So that's my competition. If I'm guessing, I better be able to get a better score than leaving it blank. All right, if I get it correct, then I get 7 points. If I'm just randomly guessing among the 5 choices, then that has a 1 in 5 chance of happening, that I guess it right. And I get 7 points in that case. On the other hand, there's a 4 in 5 chance that I guess wrong, in which case I get nothing. So that's an expected score of 7/5, which is not better than leaving it blank. My expected score is 1.4, and if I leave it blank, I get 2 points. Better bet to leave it blank. But what if I eliminate an answer choice so I know it's not A? So I know it's not A. That means that I have a 1 in 4 chance of guessing it correctly and getting 7 points. And then I have a 3 in 4 chance of guessing incorrectly and getting nothing. 7/4, which is what I would get, is 1.75. Still not above 2. And hopefully you can work ahead of me and get where this is going. Because if I eliminate another choice, and now I'm left between 3 possibilities, I have a 1/3 chance of guessing it right and getting 7 points, versus a 2/3 chance of getting it wrong and getting nothing. So that is 1/3 times 7. That's going to be 7/3, which is 2.3 repeating, which is now better than if I just guessed. So I need to get rid of 2 choices. How many must be eliminated before we're left with 3 choices, and then it's to our advantage to guess. (34). Given that it's damaged, what is the probability that it stops working? So we are finding that the probability that it stops working given damaged. Stops working given damaged. And there's a formula for that on the formula sheet. But the idea behind the formula is that we are looking at, since we are given that it's damaged, we want to look at, out of all the times that it is damaged, which is 0.1, probability that it's damaged is 0.1, out of all those times, how often did it stop working, which was 0.04. Out of all the times that it was damaged, how often did it stop working? That's 0.04 out of 0.1, which is 0.4. (35). Drinking water is considered safe when the average level is 24.5 parts per billion. So 24.5 parts per billion is what we have. and we get a sample that gives a 25.3. So our sample is what gives a 25.3. That's not what we think the parameter should be. And we are testing whether the drinking water is dangerous. We're concerned that it's unsafe levels. So if that's our concern, then we're looking at if 24.5 or less is safe, and we're testing whether it's unsafe, then our alternative should be that it's unsafe. In other words, that the mean is greater than the 24.5. So our answer there is D. 36. Correct interpretation of 19.0. 19.0 is right here. This is our slope of the line. That's our slope of the line. So interpretation of slope is that every time x goes up by 1, y is predicted to go up by 19. So in this case, a couple different clues, which one's x and which one's y. So most people were between A and B here. First off, my coefficient for slope should be attached to x. Clue number 2 is that it says in the table, response variable is zinc. So response variable is y. And if you're reading the question, it's showing the result for predicting the concentration of zinc from the concentration of lead. So we are using the lead, x, to predict the zinc, y hat. We are predicting the zinc from the lead. So lead is our explanatory variable that we are using to explain the response of zinc. So our answer there is B, since lead is our x and zinc is our y. Next. So it gives the mean and standard deviation, and then it gives samples of size 100. So this is the sampling distribution. First off, sampling distribution, since the size is 100, 100 is at least 30, which means approximately normal. As soon as our sample size is at least 30, we can say that it's an approximately normal distribution. Mean is the mean. Standard deviation is the standard deviation, the population divided by square root of n. So in this case, that would be 37,881 divided by the square root of the sample size is 100, which is 3788. So sample size is at least 30 means it's approximately normal, and then we can just use our standard deviation formula of standard deviation over square root of n. 38. Appropriate null hypothesis here. Remember that our null hypothesis should usually be a statement of equality, or a statement that there's no difference, or that there's no change, or that it equals something. So hopefully you're getting rid of A, you're getting rid of C, you're getting rid of D. Those are more alternative hypotheses. And then not the probability is 0.5. We are trying to test whether there's a difference, and so our null hypothesis should be that there is no difference, B. All right, home stretch, almost done. Let me just take a roll. Red comes out to be 1. Green comes out to be 6. Red minus green is 1 minus 6, which is -5. So that's the smallest value I could get, is that -5. The largest value I could get would be a +5. If red and green were switched and the red was 6 and the green was 1, then I would get +5. So my range of values should be between -5 and +5. That's the limits and choices right there. And then the other thing that I need to know is how likely is it that I get -5. This happens one way. The only way that happens is if red is 1 and green is 6. That's the only way I can get -5. Versus red minus green being 0. This can happen 6 ways. I could roll double 1s, double 2s, double 3s, double 4s, double 5s, double 6s. So clearly, some of these outcomes around 0 are more likely, and some of the outcomes around -4 and -5 have fewer ways to happen, so they're going to be less likely. And finally, number 40. Let me ask a related question that might help you. Let's say, since the probability of winning the game is 0.5, let's say that the game is flip a coin. All right? And you have to win the game a certain percentage of the time. So if I ask the question, I need you to flip all heads, and if you flip and get all heads, then you win my game. And I give you a certain number of flips of the coin. Would you rather play that game if I asked you to flip it 2 times and get all heads, or flip it 2,000 times to get all heads? Obviously, 2 times. And the reason that is basically the lower my sample size, the lower the amount of times I flip the coin, the more likely it is that extremely high or extremely low values are going to happen. Same idea for 70%. If I want 70% of the time to get heads, it would be better if I flipped the coin 10 times versus flipping it 10,000 times and trying to expect 7,000 or more heads. Formula-wise, remember that this standard deviation would be p times 1 minus p over n. And I want this to be as large as possible because I want values that are far away from the mean of 0.5. So if I want values that are far away from the mean, then I'm going to choose a sample size that is as small as possible so that this standard deviation is as large as possible. So either way you think about it, 10 would be my preference for the sample size. It does matter because smaller sample sizes are prone to those more extreme values more often than larger sample sizes are. And that's because as sample size goes up, spread goes down. So if I want larger spread, smaller sample size. And that is this practice multiple choice. Again, I don't expect perfect scores on these multiple choices. What I am hoping is that as you saw the method and saw these questions gone through, that things started to click in your head. Ideas started to come back. If it didn't make sense before, now it is making sense. That is what I am hoping. So that's all I have for now. If you have any questions on any of these that you're still stuck on, feel free to let me know.